We've done a couple examples of related rates problems. I want to do one last one because this one is going to be a little bit of a twist in the relationship between the two variables. So let's take a look at how this looks. So a rocket is traveling at a constant velocity of 7 miles an hour straight up, and it's being watched by a woman who is standing 5 miles away from the launch site. At the moment the rocket is at an altitude of 5 miles, we want to know at what rate is the angle of elevation of the woman's line of sight as she continues to watch the rocket. Okay, let me stop for just a second and I'll describe some of that vocabulary if it's new to you or if it's something that maybe you were exposed to a couple years ago when you first studied trig and you don't quite remember what it means. So line of sight means if I'm watching something, you can see how the gaze line that I'm doing is moving based on what I'm looking at. And angle of elevation is talking about the angle between that ray and the ground. So it's the amount that you're elevating your head, kind of, that angle to see where you're looking at. So that's what we're trying to measure in this problem. Okay, so let's go back and once again, go through the steps, pause the video and try to do it, and then unpause the video and see how I do it. So the first thing we want to do is we want to create a diagram. Okay, so our diagram is going to look like this. So here's the launch site and the rocket is going straight up. And then we've got the observer over here. And so that's kind of what's happening with the diagram right there. Okay, so let's identify the numbers. We'll create some variables and then we'll express all of these facts in calculus notation. All right, so what's changing in this problem? What things are changing over the course of time? Well, the first thing that we're talking about is the height of the rocket, its altitude above the launch site. I'll call that h. And the other thing we're talking about is the angle of elevation. So here's the angle of elevation right here. And since you're all incoming college students being prepared for serious mathematical notation, I want to use Greek letters to talk about angles. So we're going to call that angle theta. All right. The other thing we know is that the distance between the launch site and the woman is definitely 5 miles. And we know that the rate of change of the height is 7 miles per second. So we're going to write that the dh dt, the change in height over time, is equal to 7. And they want us to figure out the rate of change of the angle of elevation. So they want us to figure out d theta dt when h is equal to 5 miles. Okay? So those are the problems that we need to figure out. The next step of the problem is to come up with an equation that ties theta and h together. So what do we know about theta and h? And the 5. Once again, this is a right triangle. If we were interested in knowing the distance between the rocket and the woman, we would use the Pythagorean theorem. But this time, since we're talking about that angle, what we want to use is a trig definition. So what's the trig relation that's going to compare the h and the 5, the two things that we know? Well, these are the opposite and the adjacent sides of the triangle relative to angle theta. So that is that the tangent of theta is equal to h over 5. And just to make it a little bit more clear, I'll write that as 1 over 5 times h. Because the next thing that we need to do is we need to implicitly differentiate this equation with respect to time. So think about how to do that. Okay, so the derivative of tangent theta with respect to theta, this is one of the things that's in our derivative reference sheet, and eventually you'll need to memorize it. But the derivative of tangent of theta is secant squared of theta. And so the derivative of this with respect to time is secant squared theta d theta dt. All right. And on this side of the equation, we're differentiating 1/5 h with respect to t. And so that's going to be 1/5 times dh dt. You could take the derivative of it written like this, but this might make it a little bit more clear that this is a linear equation with a coefficient of 1/5. All right, so now we can start substituting in values. So I know that dh dt is equal to 7. So that's equal to 1/5 times 7. D theta dt is what we need to solve for. And so the other thing that's here is secant squared of theta. So I don't know a ton about secant. So the first thing I want to do is I want to turn it into something involving sine or cosine. I'm much more comfortable with that. So secant is the reciprocal of cosine. So this is going to be 1 over cosine squared theta. All right. And now, just because we want to solve for d theta dt, I might as well multiply both sides by cosine squared of theta. So d theta dt is equal to 7/5 times cosine squared of theta. So how can we figure out what theta is, or alternatively, what cosine of theta is? We could do either one of those things. What extra fact do we know? Well, this is the case for any time. This is the equation that you would use to come up with d theta dt, but we know that we're doing this at the moment that the altitude of the rocket is 5 miles. So in this case, we've got that's 5, we've got this is theta, and this side is also 5. Okay, so we can figure out what theta is. That's a 45-degree angle, or pi over 4 radians. We could think of it either in those ways. Just for kicks, I want to jump forward and calculate cosine of theta directly. So cosine is adjacent over hypotenuse. So cosine theta is equal to the adjacent over the hypotenuse. And what's the hypotenuse of this right triangle? Well, we've got 5 squared plus 5 squared is equal to the hypotenuse squared. 5 squared is 25. 25 plus 25 is 50, so the hypotenuse is going to be the square root of 50. So the cosine of theta is equal to the adjacent is 5, and the hypotenuse is the square root of 50. So substituting that into our equation here, we've got that is equal to 7/5 times 5 over the square root of 50 squared. And how do we simplify this? Well, 5 squared is 25 in the numerator, and the square root of 50 squared is 50. So that'll settle out like that. And so multiplying it all together, d theta dt is equal to 7/10. Now here's the question that I have. What's our units for this? What unit are we using to talk about the derivative of the angle with respect to time? Time, we could see that we're measuring time in seconds. So that one's easy. But if you think this is 7/10 degrees per second, you're wrong, because we don't calculate trig functions in degrees. The reason the tangent of theta, the reason the derivative of that is secant squared of theta without some sort of linear multiplier in front of it, is because we are measuring this in radians. Radian measure is the reason that the derivative is easy to memorize. And so we have to be sure that the change in angle is 7/10 radians per second. All right, so that is a key idea to keep in mind when you're talking about angles in calculus problems. So that was a cool problem for a couple different reasons. First of all, it involved a trig relation. So we needed to remember some trig identities. We needed to remember the trig derivative rules. And we also needed to remember that when we use trig, our way of measuring angles is always in radians. If you wanted to think, well, what's cosine of theta, you could have looked at this isosceles triangle and you could have thought to yourself, well, this is 5 over 5, so this is 45 degrees, and I can calculate, I can plug the cosine of 45 degrees into my calculator. At that point, that's not a problem. But the problem is that when you get to this spot, you need to be sure that we're measuring the angle in radians instead of degrees.